Hi, my name is Nelly Patricia and my metric number is A810943. I will start this presentation with introduction of equilibrium in rigid body. Rigid bodies are those bodies in which the distance between particles is constant despite any kind of its external force. So, while studying the equilibrium of rigid bodies, we mainly aim to define the behavior of these constituting particles in change conditions of force or torque. Since we are concentrating on the equilibrium of rigid bodies under motion, therefore we need to take both translational and rotational motion into consideration. In the mechanical equilibrium of a rigid body, the linear momentum and angular momentum remain unchanged with time. This implies that the body under the influence of external force neither has a linear acceleration nor an angular acceleration. We therefore can say that if the total force on a rigid body is zero, then the body shows translational equilibrium as the linear momentum remains unchanged despite the change in time. If the total torque on a rigid body is zero, then the body shows rotational equilibrium as the angular momentum does not change with time.
Hi, Assalamualaikum. My name is Muhammad Luman Hakim bin Abdul Aziz, AA211045. So I will discuss about additional theory. A rigid body is said to be in equilibrium if it has neither linear acceleration nor rotational acceleration. According to Newton's law, the absence of linear acceleration requires that the vector sum of all force be zero, which is sum F equal to zero. It is called the first condition of equilibrium. According to Newton's second law for rotation, the absence of rotational acceleration requires that the vector sum of all torques be zero, which is sum t equal to zero. It is called the second condition of equilibrium. In this experiment, all force be in a single plane. One consequence of this is that the vector equation label may be replaced by two scalar equations. Another consequence is that all torques are either clockwise or counterclockwise. The vector sum of equation then becomes a scalar or algebraic sum, greatly simplifying the calculation. So now we will discuss about procedure. For setup A, point load along the beam. First, the work panel in the vertical position is secure as shown in figure 2. The center hook is adjusted until the hole in the center of the beam is lined up with the work panel board hole. Third, the spring balance is attached to the upper hole of each end of the beam with their scales at the ends furthest from the beam. The weight hanger is lifted off from the beam, but one hook is left at the furthest left hole of the beam. Number four, a distance of A is set as 0 meter and B is set to the last hole, which is 0.36 meter. The length is then 0.36 meter. The balance scale is set to 0 while it supports the beam's weight. And last one, load of 49 multiplied by 10 gram masses is placed to weight hanger A and B, giving a total weight of 500 gram, 4.9 Newton on the weight hanger. The balance tabs is adjusted to make the beam level. The reading of spring balance RA and RB is recorded. For setup B, which is uniformly distributed load, first, the work panel in the vertical position is secure as shown in figure 3. Second, the center hook is adjusted until the hole in the center of the beam are lined up with the work panel board hole. Third, the spring balance is attached to the upper hole at each end of the beam with their scales at the ends furthest from the beam. Five hooks are left at five evenly spaced positions along the beam. The length is then 0.36 meter. The balance scale is set to 0 while it supported the beam's weight. 4. The load 4 multiplied by 10 gram masses is placed to each weight hanger giving a total of 50 gram on each weight hanger and on overall uniformly distributed load of 250 gram. The 5 weight is added to the hooks and the reading of spring balance RA and RB is recorded. And last one, the beam and load apparatus is set up as in table 3 and the reading of spring balance RA and RB is recorded.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amin Wasif bin Ghazali and my metric number AA212283. So now I want to answer the question. So first question is explain the sum of the reaction force for the point along the beam irrespective of where the load is. Okay, as we can observe throughout the experiment, the sum of all reaction force along the beam is always the same and equal to the weight of load irrespective of the placement of the load. This is because according to Newton's third law, every applied force will always have an opposite reaction force with the similar magnitude. So regardless of the placement of the load, as long as the weight of the load is the same and no additional external force is acting on it, the total sum of all reaction force for the point along the beam will always equal to the weight of the load and same throughout the experiment. So for the next question is consider the case where UDL runs from directly under the support to the center of the beam. Could you consider the load to be concentrated? Would RA and RB be equal? Okay, so the area that will be concentrated is in the middle of one end to the center of the beam. If UDL runs directly under the support from both ends to the center of the beam, then the value of RA and RB would be equal. However, if UDL runs from one end only to the center of the beam, then RA and RB would be different. So for the last question is what type of load would be carried by the beam supporting the roof if a heavy snow fall on a flat roof. So type of if a heavy snow fall on a flat roof is no load. It can be imposed by the accumulation of snow. It is more of a concern in geographic regions where snowfall can be heavy and frequently. The shape of a roof is particularly important factor in the magnitude of the snow load.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Saifuddin bin Ahmad Kawahi and my matrix number is AA211411. Today, I will talk about a discussion in the experiment equilibrium of a rigid body. So, the first discussion is discuss the value of RA, RB and RA plus B can be obtained. In setup A, the value of RA, RB and RA plus RB are the same experimental and theoretically. It shows that when the distance between weight hangers from both ends is the same, the value of RA and RB remains unchanged. In conclusion, RA equal with RB. In setup B, the value of RA, RB and RA plus RB are the same. This is due to the spread out of the beam. It has caused it to be uniformly distributed. So, the second discussion is compare experimental and theoretical value for the point along the beam. If not same, why? The answer is the result of experimental and theoretical value for the point along the beam is the same as the showing above. The result of the experiment that we get is 4.9 Newton for both spring balance throughout the experiment. When using the calculation that according to the theory, the calculated value is the same as the experimental value, which is 4.9 Newton. So, the last discussion is if the weight of the beam was an important factor to be considered, how would you include it in a calculation? So the answer is, if the weight of the beam was an important factor to be considered, we must calculate or record the weight of the beam, not including the load that will be added. In calculation, the final weight must be minus with the weight of the beam to get a clean weight of the load that we want to serve. For example, if the final weight is 4.9 Newton, it must be minus with the weight of the beam, so that the lead that we get is consists the weight of load only. We have to repeat the process to get the average value. That's it for me. Thank you.